Hello friends, this is my second video in the series DS and Algo for competitive programming. In the last video, I gave you an idea about how binary search works. In this video, I will take up a coding problem that can be solved using binary search. So let's start. Here is the problem statement. Count negative numbers in a sorted grid. Given a m into n grid sorted in non-increasing or descending order, both row-wise and column-wise, return the number of negative numbers in the grid. One thing to remember here is that both the column and the rows are sorted in descending order or non-increasing order. This problem can be categorized as easy if you solve it with a simple iterative approach. But this will be categorized as medium level problem if we use binary search for solving it. This is one of the most commonly asked binary search problems in the coding interviews. So let's try to solve this problem first with the simplest iterative approach and then with the binary search. And then let's try to optimize the binary search solution as well. Now let's go through the simple iterative approach. In this approach, we basically go through all the elements in the grid, and then whenever we encounter a negative value, we basically increase our counter variable by 1. As you have noticed that in this approach, we basically have to go through all the elements in the grid. So the time complexity of this approach is order m into n. If we talk about the space complexity of this approach, so we are just introducing an additional variable for storing the count of negative numbers. So the space complexity of this approach is order 1. And the main advantage of this approach is that it basically works even if your grid is not sorted. Now let's talk about the simple binary search solution. In the simple binary search approach, we basically go through each and every row in the grid and then we perform binary search on that row. This method, find first negative element in the row, is responsible for performing binary search on the row represented by index I. So we basically go through each and every row and then this method performs binary search on that row. The pattern to consider here is if we have found a negative element at index j in the ith row, then all the elements following the element at index j in the same row will always be negative. If the element at index j is the first negative element, then we return j. Otherwise, we look for the first negative element on the left side of index j. Now let's talk about the time complexity of the solution. As discussed in my last lecture, the time complexity of performing binary search on an array of size n is order log n. If we want to perform binary search on m arrays of size n, then the time complexity becomes order m into log n. As we all know that we can consider a two-dimensional array as a collection of one-dimensional arrays. So the time complexity of performing binary search on a two-dimensional array of m rows and n columns becomes order of m into log n, and hence the time complexity of this approach is order m into log n. I have an assignment for all of you. I would request all of you to comment on the space complexity of this solution in the comment section of this video. Just a small hint that the space complexity will be different for the iterative and recursive approach. You can refer to my previous video on binary search for description on space complexity. In the previous section, I have used a method find first negative element in the row, but I left this method unimplemented. I would request all of you to please try and implement this method on your own. I'll provide the link to this problem in the description section of this video. The suggested time limit to implement this method is 30 to 60 minutes. But even if you take more time than 60 minutes, it is completely fine. Now let's jump into the code. As you can see on line number 16, we are provided with a sorted two-dimensional array as an input. On line number 17, we just check if the input array is null or empty. If this is the case, we return 0. On line number 21, we are iterating through every row in the input two-dimensional array. On line number 22, you can see that we are calling a method find first negative element in the row with 0 as the start index and last index of the row as the end index. We are performing binary search on the entire row here. The method find first negative element in the row returns -1 if no negative element is found, and it returns the index of the first negative element in the row if the negative elements are present. If negative values are present in the row, this index variable represents the index of the first negative value in the row. If we subtract this index from the number of elements in the row, we basically get the number of negative elements in the row. We use this variable negative number count to keep track of the number of negative values in our two-dimensional array. And after iterating through each and every row, we return this variable as our result. Now let's talk about this method find first negative element in the row. This method find first negative element in the row is quite similar to the one we have implemented in my previous lecture. What we are trying to do in this method is we are trying to find a middle element, and then we basically check if it is smaller or greater than 0. On line number 47, as you can see that we are finding the middle element, or actually the index of middle element. On line number 49, we check if this index is equal to 0 and the value at this index is less than 0. In this case, we simply return 0. On line number 53, you can see that we are checking if the value at index mid is less than 0, but the value at index mid -1 is greater than 0. In this case, we basically return mid because there are no negative elements on its left side. On line number 57, we check if the element at index mid is less than 0. In this case, we basically look for more negative elements on its left side. But if the element at index mid is greater than 0, then we look for negative element on its right side. Now, after going through this code line by line and understanding the approach that we have taken up for solving this problem, I would ask all of you to take 2 to 3 minutes and think about the possible optimization that we could do over our current solution. Here are the optimizations that I could think of. If the first negative element in a row is at index j, then in the next row, we should not consider the entire row for binary search. We should only consider the subarray starting at column index 0 and ending at column index j. Now let's talk about the second optimization. If the first element of any row is negative, then all the element in that row and the following rows will be negative. Take a moment and think about it. If the first element of a row is negative, then all the elements in the same row will be negative as the rows are sorted in descending order. And all the elements below this negative element will also be negative because the columns are also sorted in descending order. So if the first element of all the rows below this element are negative, then all the elements following them will also be negative. Now let's go through the optimized solution. The method signatures are exactly the same as discussed in the previous solution. The important thing to note here are the variables end column index and column count. End column index contributes to the optimization number 1 discussed in the previous section, whereas column count contributes to the optimization number 2 discussed earlier. The condition on line number 36 represents the case where the first negative element is present at index 0, which means that all the elements in this row will be negative, as well as all the elements in the subsequent rows will also be negative. So we just have to add the number of elements in this row and the subsequent rows to the negative number count, and then we basically return the final value of this variable. The condition on line number 40 represents the case where we have found a negative element in the row. In the next line, we add the number of negative elements in the row to the variable negative number count, and then in the subsequent line, we set the value of variable end column index to the index at which the first negative value for this row was found. For the next row, we only have to consider the subarray starting at index 0 and ending at index represented by variable end column index. I will provide a link to my GitHub repository in the description section of this video. In my GitHub repository, you will be seeing two classes which are actually solving this problem. This class is without optimization. So it basically contains the code with a simple binary search approach where we go through each and every row and then we try to perform binary search on the entire row. Whereas this class is the one with the optimizations that we have discussed in the previous section. Just remember that even with optimization, the worst case time complexity of this algorithm would be order m into log n. Now we are almost at the end of this video. Just remember the problem that we have discussed today is very important for coding interviews. I hope you are able to solve this problem on your own. In the next few videos, our focus will be entirely on binary search. I'll provide a link where you can solve this problem in the description section of this video. I'll soon come up with a new problem on binary search and we will try to solve it together. If you like the content of this video, please like and subscribe. If you have any suggestions for me, please write them down in the comment section of this video. Hope to see you soon. Goodbye for now.